Welcome to our sit online. I'm Dr Asha Vishwanath, Department of Civil Engineering, and we're looking at Dynamics Module 5 of EST100 for the first years. And this is Part 4, which is curvilinear motion. And in this section, we'll be looking at kinetics. Now, the kinetics, as we all know, is the study of forces acting on the body. Now, as we said, that the path traversed by a body, when the path is curved, we call it a curvilinear motion. So when a body passes through a curvilinear motion, what are the effects of forces on it, or what are the forces acting on the body is what we will study in the kinetics of curvilinear motion. And just like the kinetics of rectilinear motion, we will also be looking at D'Alembert's principle for curvilinear translation. Now, when a body passes through a curve, that is like a cyclist going in a curved path, or a pendulum which is having a curved trajectory, we find that the equation of motion, just like we discussed in the rectilinear motion, is F is equal to ma using the Newton's second law. Now, in this case, what happens is the motion is through a curved path, and hence the velocity will have two components, which is one along the path that it would have traveled if it was a linear path, that is called the tangential, because it will be tangential to each and every point of the curved path. And that is exactly the same velocity that it would have undergone if the path was straight. So it is given by the same value or by the same acceleration value. That is, the acceleration in that particular direction, or the tangential acceleration, will just simply be equal to d of dt by dt. Now, this velocity is the tangential velocity, but at the same time there is another component of the velocity which is acting normal to it, that is, which is perpendicular to this tangential velocity or acting along the radius of the path. Now, one velocity will be tangential while the other will act along the radius. Now, this velocity, as we know, it would have been a straight velocity if the particle had continued in its path of straight line. But because it is changed, it is also having a radial velocity. So now this radial velocity also creates a radial acceleration. Now this is called a normal acceleration, which is given by mv square by r, which is different from the tangential acceleration as we have seen before. So this tangential and normal acceleration are two components of the acceleration which will be acting on the body when the body undergoes motion in a curved path. Now, forces corresponding to these acceleration would simply be F is equal to ma as per Newton's second law. So, because we have both in the x direction and the y direction, or in the normal direction and the tangential direction, we can call that we have two forces, one in the normal direction and one in the tangential direction, and which will be given by their corresponding accelerations. Now, the same a principle of D'Alembert's principle for rectilinear motion can be applied in this case as well, in which we consider that this ma is only an inertia force which is preventing the motion of the body in the direction of that force. So when it prevents it, by virtue of its mass, it is being resisted, and that is inertia, and hence the ma can be considered as an inertia force in the D'Alembert's principle, and hence rewritten as F plus minus ma, and stated as that all the net force acting on the body, including the inertia force, is zero, or the net force acting on the body is in dynamic equilibrium with the inertia force. Now, this will happen in both the x direction and the y direction, or the normal direction and the tangential direction. Now, this is the D'Alembert's principle for curvilinear motion. Now, in this case, we will also be looking at problems of a pendulum and of a body traversing a curved path, a curved road. Thank you.